This video is an introduction to parametric equations, the concept and their coordinate geometry. Most of the time in your maths careers so far, you've been dealing with Cartesian equations. And what I mean by that is the y is directly related to the x. However, there are some situations where that's no longer appropriate, and instead, both the y and the x are going to be related to a different variable called a parameter, hence why we call them parametric equations. So over here we can see we've got this heart, and the equation of that heart is expressed parametrically as x equals 16 sine cubed t, and y is 13 cos t, blah, 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 as you can see there. The x and the y both depend on a separate variable, t. That's the parameter. And that has created that heart shape. You can see here we have a set of values of t that we substitute into the x and the y. We call that the domain. We'll talk more about domain when we do the functions unit. A concrete example of something you're going to do a lot in your mechanics is projectile motion, where the x coordinate and the y coordinate are both dependent on a separate variable, the time that has passed whilst that projectile has been in the air. So in that situation, it is useful to use parametric equations rather than Cartesian equations. So let's have a look at a simple example. Here I've got the parametric equations, x equals 2t squared minus 3, and y equals a half t cubed. And I'm given the domain as being between, t as being between minus 2 and 3. Now we could do this with a table of values. So here I have taken the domain of minus 2 to 3. And then all I've done is I've substituted the t value into the x equation. So 2 times minus 2 squared minus 3 is 5. Then I've done the same thing with the y. I've done a half times minus 2 cubed and got the minus 4. So when t is minus 2, the x coordinate is 5 and the y coordinate is minus 4. So I can plot that onto my graph here. This point here, the coordinate 5 minus 4, that's when t is minus 2. And you can see in the table over here, I've done the same thing when t is minus 1. So I've got the x coordinate minus 1, the y coordinate minus a half, which is roughly here. Then when t is 0, I got the coordinate minus 3, 0. When t was 1, I got the coordinate minus 1 a half, which is here. When t was 2, I got the coordinate 5, 4, which is here. And then when t was 3, I got the coordinate 15, 13.5. So that is roughly over here. And so, to sketch this then, drawing a smooth curve through those points. This is what the curve that's defined by the equations x equals 2t squared minus 3 and y equals a half t cubed between the values of t being minus 2 and 3. That's what it would look like. And you could do the usual sorts of things with coordinate geometry here. If I wanted to work out where it intercepted on the y-axis, I can make the x coordinate 0 there. make the x coordinate 0, and then I'd be able to work out what t is at that point. And once I know the t value at that point, I could substitute it into here to get the y coordinate at that point. And we're going to see over the next few lessons how we could work out the equations of tangents, or work out the area underneath these curves by using integration and differentiation. Right, let's look at a slightly more complicated example. So here I've got the parametric equations, x equals t cos t and y equals t sine t. And the interval I'm looking at is the values between 0 and 2 pi. So again, I could set up a table of values for this, just like I did a moment ago. And pick some values of t, substitute the t into here and here to get the x coordinate, substitute it into here and here to get the y coordinate, and then start plotting these points. Just to make this a bit quicker though, I'm actually going to show you this on the Desmos app. So you can see in the top left there, next to the purple dot, we've got the x being defined as t cos t and the y being defined as t sine t. Currently, I've said that t is 0, and you can see that that has given me the point 0, 0 on our graph here. If I start to increase the value of t, we can see that it's giving me different values of the x and the y coordinates. So when t is 1, 1 times cos 1 is 0.54. 1 times sine 1 is 0.841. And as I keep increasing the value of t, we're plotting out a curve. And you can hopefully start to see what type of shape this is making. Let me do this again for you one more time. To show you that in full, it was a spiral. So the parametric equations, x equals t cos t and y equals t sine t, between the values of 0 and 2 pi, give that spiral. What about if I was to start to change this domain? What about if we were to go from 0 to 3 pi instead? It would look like that. Or 4 pi would look like that. Or 5 pi, and so on. So we could change the domain, the values of t that we substitute in here, to get more of the curve. Second example on Desmos here. Here I've got the x coordinate that is given by 6 cos t plus 4, and the y coordinate is given by 6 sine t minus 1. And currently I've just got it set so that t is between 0 and 1. You can see we've got this arc. If I increase the value of t here, so now this is between 0 and 2, we've got more of the arc, between 0 and 3, between 0 and 4, and 5, and 6. You can see this is forming a circle. And when I get to 0 and 2 pi, we have a full circle. Because cos 2 pi is the same thing as cos 0. Sine 2 pi is the same thing as sine 0. So once I go to 2 pi, I get back to where I started from. And so the x and the y coordinates are the same. And similarly, if I change this to be 3 pi, you'll notice the circle doesn't appear like it's changing at all. If I change to 4 pi, again, it's the same thing, because we're just going round and round the circle. So actually all we need is just 0 and 2 pi in the domain to get a full circle. Now obviously we're used to using the equation x minus a squared plus y minus b squared equals the radius squared for a circle. And in the next lesson, we'll see how we can take these parametric equations and turn them into our Cartesian equations to work out the centre of the circle and the radius of the circle. Right, let's have a look at an example of coordinate geometry. Here we've been told that the curve C is defined by the parametric equations x equals 4t squared minus 16, y equals kt plus 1, where t is between minus 3 and 5, and k is a positive constant. Part A, given that the curve intersects the y-axis at the points when y equals 7, find the value of k. Just to speed up this video, I've already shown my working out here that I will just talk you through. So when it said intersects the y-axis, that's telling me that x equals 0. So we've got the coordinate 0, 7. So what I've done is I've taken my x parametric equation and made that equal to 0, which has then told me that the curve will have x coordinate 0 in two places, when t is 2 or when t is minus 2. So there's two different values of t that give me an x coordinate of 0. I've then looked at the y coordinate. So I know the y coordinate is 7. So my y parametric equation, the kt plus 1, will have to equal 7. So therefore kt equals 6, that's me subtracting 1 from both sides. And then I'm thinking, I know that t is either 2 or minus 2. And I know that t is going to have to be positive 2, because that gives me k being 3, which is a positive constant. If actually I had chosen t to be minus 2, I'd have had k times minus 2, which would have been 6, which would have meant that k would have had to have been negative 3, which wouldn't have been sensible for this question. So that's how I worked out the value of k. Part B, we need to find where the curve intersects the x-axis. So, intersecting the x-axis, that's telling me that the y-coordinate is equal to 0. So I've then taken my y equation, which I now know, because I worked out previously that k was 3. So my y equation is now 3t plus 1. And I've made that equal to 0 to find when the y-coordinate is equal to 0 and where the curve intersects on the x-axis. I've then solved that equation to find that t is minus 1/3 at that point. And then I've just substituted that value of t into my x equation. So 4 times minus 1/3 squared minus 16 is minus 140 over 9. And so that is the x-coordinate when the y-coordinate is 0. So that's where the curve would intersect on the x-axis. Part C, we had to find the value of t at the point 9 minus 6.5. So my x-coordinate is 9. So I've taken my x parametric equation and made it equal to 9, which I've then solved to find there's actually two places where the x-coordinate is 9, when t is either positive 2.5 or negative 2.5. At both of those values of t, the x-coordinate would equal 9. I've then checked out the y-coordinate, because I know the y-coordinate is minus 6.5. So I've made my y equation, my y parametric equation, equal to minus 6.5. And then I've solved that to find that y would equal minus 6.5 when t is minus 2.5. And we can see that value of t does give me the coordinate 9 minus 6.5. And so that is the value of t that I want. When t is minus 2.5, the x-coordinate is 9, and the y-coordinate is minus 6.5. When t is positive 2.5, the x-coordinate is 9, but the y-coordinate would not be equal to minus 6.5. It would be equal to 8.5. And then part D, we have to find the coordinates where the curve intersects the line 4y equals 3x plus 43. So the curve intersecting a straight line. So we're doing simultaneous equations. And so what I've done here is I'm using the substitution method. I know that y is equal to 3t plus 1. So I've substituted that in here to get 4 lots of the 3t plus 1. Similarly, I know that the x is going to be equal to the 4t minus 16. So I've substituted that in here. I've then expanded these brackets, expanded these brackets, put everything onto one side of the equation, divided each term by 3 there, just to make this quadratic a bit easier to solve. I've then factorised it, and found the two values of t as being minus 1/2 and 3/2. So those are the two values of t where my parametric curve intersects this straight line. I actually wanted the coordinates though. I don't actually want the values of the t. I don't want the values of the parameter. I want the coordinates. So what I've then done is I've substituted my parameter into my x equation, the 4 times t squared minus 16, so 4 times minus 1/2 squared minus 16 is minus 15. And I've then substituted the t parameter, the minus 1/2, into my y equation. 3 times minus 1/2 plus 1 is minus 1/2. So when t is equal to minus 1/2, the curve intersects the straight line, and that is the coordinate. And then I just did exactly the same thing with the other value of t where the curve intersects the line, and found the x-coordinate is minus 7 and the y-coordinate is 11/2. So this is the other coordinates where the line intersects the curve. So that is parametric equations, their concept, why we use them, and an example of some coordinate geometry.